Look up at the night sky, and you'll see countless stars shining peacefully. But hidden among them are cosmic ghosts, planetary nebulae, each one a dying star's final breath, twisted into shapes stranger than anything we could imagine. These glowing masterpieces aren't just beautiful, they're hiding secrets that defy the laws of physics as we know them. Picture a butterfly with wings spanning light years, or a spider's web woven from hypersonic shock waves. Imagine a nebula so cold it's just 1 degree warmer than absolute zero, the chill of deep space itself. These aren't science fiction, they're real, and they're lurking in our galaxy. Today, we're pulling back the curtain on 25 of the most mind-bending discoveries about planetary nebulae, cosmic riddles that have left astronomers scratching their heads. From a nebula vanishing before our eyes to mysterious dark matter whispers shaping their forms, you're about to see the universe in a way you never have before. Stick around, because by the end of this journey, you'll never look at the night sky the same way again. Now let's zoom in on our first cosmic wonder, a nebula so breathtaking it could only be named after one of nature's most delicate creatures. The Butterfly Nebula, officially known as NGC 6302, is anything but fragile. This celestial masterpiece stretches its wings across space with a symmetry so precise it looks almost sculpted by an artist. But don't let its beauty fool you. What we're seeing is the aftermath of a star's violent death throes, a spectacle that challenges everything we thought we knew about how nebulae form. What makes the Butterfly Nebula truly jaw-dropping are those enormous, wing-like structures, each one a bipolar jet of gas screaming outward at speeds of up to 600,000 miles per hour. To put that in perspective, that's fast enough to travel from Earth to the Moon in under half an hour. These jets aren't just random bursts of energy. They're channeled and shaped by something invisible yet incredibly powerful: magnetic fields. Astronomers believe the star at the heart of this nebula didn't just die quietly. It likely had a companion, a second star, or even a massive planet whose gravitational dance disrupted its final moments. As the dying star expelled its outer layers, its magnetic field acted like an invisible funnel, squeezing the escaping gas into those two opposing jets. The result, a structure so perfectly symmetrical, it defies the chaotic nature of most stellar deaths. But here's where it gets even wilder. The Butterfly Nebula's wings aren't just expanding, they're also twisting, creating intricate patterns that resemble cosmic ribbons. This twisting motion suggests the star was spinning rapidly as it died, adding yet another layer of complexity to this already enigmatic object. And while most planetary nebulae fade over thousands of years, the butterfly's extreme speeds mean it's evolving right before our eyes, offering astronomers a rare glimpse into the real-time death of a star. So next time you hear the name Butterfly Nebula, don't just picture a delicate insect. Think of a star's final, furious act, a cosmic explosion tamed into symmetry by unseen forces, proving once again that the universe loves to surprise us. This isn't just a nebula, it's a lesson in how much we still have to learn about the forces shaping our galaxy. Now let's unravel another cosmic enigma, one that spins a far more turbulent tale than its delicate name suggests. The Red Spider Nebula, catalogued as NGC 6537, is anything but serene. This sprawling, tangled web of gas stretches across space with a chaotic beauty, its fiery hues painting a scene of celestial violence. Unlike the Butterfly Nebula's precise symmetry, the Red Spider's structure is wild, as if the universe itself threw a handful of glowing filaments into the void and let them collide. At the heart of this cosmic spiderweb lies a furious dance between two stars, a binary system locked in a gravitational tug-of-war. Astronomers believe the primary star, a white dwarf, is relentlessly stripping material from its companion, a process that doesn't just feed the dwarf but also superheats the stolen gas. This creates a scorching wind blasting outward at mind-bending speeds, sculpting the nebula's intricate web-like tendrils. But what truly sets the red spider apart isn't just its shape, it's the shock waves racing through its veins. Recent observations reveal waves of energy surging through the nebula at 300 kilometers per second, so fast they could circle Earth's equator in just over 2 minutes. These aren't gentle ripples, they're hypersonic tsunamis born from the violent interactions of the binary stars. As the white dwarf's fierce winds collide with slower-moving gas ejected earlier, they create explosive pressure fronts visible as shimmering ripples in the nebula's structure. The result, a cosmic battlefield where gas is heated to millions of degrees, glowing in vivid reds and blues. What's even more fascinating is how these shock waves act like cosmic archaeologists. By studying their speed and paths, astronomers can peel back the nebula's history, uncovering clues about the star system's explosive past. For instance, the wave's uneven distribution hints at sporadic outbursts, moments when the white dwarf devoured material in frantic bursts rather than a steady stream. It's as if the star's deadly partnership has left behind a fingerprint of its chaos, written in light and motion. The Red Spider Nebula challenges our assumptions about how planetary nebulae evolve. While many fade gracefully, this one remains a churning cauldron of activity, energized by its dueling stars. And unlike the butterfly's elegant symmetry, the red spider's beauty lies in its untamed fury, a reminder that even in death, stars can unleash forces beyond imagination. So next time you gaze at this cosmic arachnid, remember, its web isn't spun from silk, but from the shock waves of a stellar struggle that's still raging across the cosmos. Moving from the chaotic fury of the Red Spider Nebula, let's turn our gaze to a cosmic spectacle that feels almost ghostly in comparison. The Helix Nebula, also known as NGC 7293, is one of the closest planetary nebulae to Earth, yet it holds mysteries that defy easy explanation. At first glance, its vast, glowing ring resembles a giant eye staring back at us from the depths of space. But zoom in closer, and you'll find something even more intriguing: dozens of eerie, comet-like knots scattered throughout its expanse, each one glowing with an otherworldly light. These peculiar structures, nicknamed cometary knots, are anything but ordinary. Each one is a dense clump of gas and dust, stretching across billions of kilometers, with glowing heads and long, faint tails that stream away from the nebula's central star. What makes them so baffling is their survival. Planetary nebulae are often thought of as fleeting cosmic events, where the ejected material disperses into space relatively quickly. But the Helix's knots have endured for tens of thousands of years, outlasting the nebula's initial violent expulsion. So how do these fragile-looking structures persist for so long? One leading theory suggests they're the result of a cosmic balancing act. As the dying star at the heart of the Helix Nebula shed its outer layers, some regions of gas may have cooled and condensed faster than others, forming dense pockets. These pockets then acted like shields, protecting the material inside from the star's intense ultraviolet radiation and fierce stellar winds. Over time, the radiation sculpted the gas into those distinctive comet-like shapes, eroding the outer layers while leaving the denser cores intact. But there's another twist. Observations reveal that the knots aren't just passive survivors, they're actively evolving. The central star's ultraviolet light ionizes the gas around them, causing the knots to glow in vivid blues and greens. Meanwhile, their tails stretch outward like cosmic windsocks, pointing directly away from the star, a clear sign of the relentless pressure exerted by the stellar radiation. Some astronomers even speculate that these knots might eventually give birth to new solar systems, as their dense cores could one day collapse to form planets or even brown dwarfs. What's truly astonishing is the scale of these formations. Each knot is larger than our entire solar system, with masses comparable to Earth's, and yet, despite their size, they're delicate enough to be shaped by forces as subtle as starlight. The Helix nebula's knots challenge our understanding of how structure emerges in chaos, proving that even in the aftermath of a star's death, nature finds ways to create astonishing complexity. So the next time you see an image of the Helix Nebula, don't just admire its eerie glow. Look for those tiny, glowing knots, each one a testament to the delicate balance between destruction and creation, and a reminder that the universe's most beautiful mysteries often lie in the details. Now, just when you think you've seen the most elegant cosmic illusions, the Ring Nebula steps into the spotlight. Officially catalogued as M57, this celestial wonder is often held up as the textbook example of a planetary nebula, a perfect glowing ring suspended in space. But here's the cosmic curveball. The Ring Nebula is anything but simple. Peer beyond its iconic shape, and you'll uncover a labyrinth of hidden intricacies that defy its pristine reputation. At first glance, the Ring Nebula lives up to its name. Its symmetrical, donut-like appearance makes it a favorite for amateur astronomers and a staple in astronomy guides. But when astronomers trained powerful telescopes like Hubble on this object, they uncovered a far more chaotic reality. That smooth ring, it's actually a tangled web of delicate gas filaments, twisted and braided like cosmic thread. These filaments glow in vivid hues of blue and green, energized by the ultraviolet light of the nebula's central white dwarf. And if that weren't enough, the nebula's core isn't a hollow space. It's a football-shaped region of scorching gas, stretched asymmetrically by forces we're still working to understand. So how did this apparent simplicity give way to such complexity? The answer lies in the death throes of the star that created it. As the star shed its outer layers, the expelled gas didn't drift away uniformly. Instead, it collided with older, slower-moving material ejected in earlier phases, creating shock waves that sculpted the gas into those intricate filaments. Meanwhile, the central star's intense radiation and winds carved out the cavity we see, but not evenly. The football-shaped core suggests that the star might have expelled material more vigorously along its poles, or that it's wobbling like a spinning top, distorting the nebula's inner structure. But the surprises don't stop there. Recent studies reveal that the Ring Nebula is more like a layered cosmic onion. Deeper observations show faint outer halos of gas that extend far beyond the bright ring, evidence of multiple outbursts from the dying star over thousands of years. These halos are the ghostly echoes of the star's final acts, a reminder that even the cleanest-looking cosmic objects have messy, turbulent histories. What's truly remarkable is how this nebula fools the eye. From a distance, it's a pristine circle, a symbol of cosmic order. Up close, it's a storm of activity, with gas racing outward at tens of thousands of kilometers per hour. The Ring Nebula teaches us that in space, first impressions are often illusions. What looks like a quiet, orderly farewell is actually a dynamic, multifaceted spectacle, proving that even the most familiar objects in the sky still have secrets to share. So the next time you gaze at the Ring Nebula, remember, you're not just seeing a ring, you're witnessing a cosmic masterpiece where every fold of gas and every asymmetry tells a story of stellar death and the breathtaking complexity it leaves behind. Just when you think the cosmos has shown you all its tricks, the Cat's Eye Nebula pulls you deeper into its hypnotic layers. Officially known as NGC 6543, this nebula is one of the most complex planetary nebulae ever discovered, and its mesmerizing concentric shells tell a story of cosmic violence and rebirth. At first glance, the Cat's Eye appears as its name suggests, a glowing feline pupil surrounded by intricate rings, but zoom in and you'll discover not one, but 11 distinct shells expanding outward like ripples in a pond. These nested layers aren't just for show, they're cosmic breadcrumbs leading back to the dying star's final, turbulent millennia. Each shell represents a violent episode where the star blasted massive amounts of gas and dust into space, only to repeat the process again centuries later. What could cause such rhythmic destruction? Imagine a star not just dying but convulsing. unlike the steady exhale of most dying stars, the cat's eye's progenitor star seems to have experienced fits of extreme mass loss. During each outburst, it ejected material equivalent to the entire mass of Earth, or more, into space at incredible speeds. Then, after a brief lull, another eruption would occur, inflating a new shell inside the previous one. The result, an expanding cosmic matryoshka doll frozen in time. Hubble Space Telescope observations reveal even wilder details. The innermost shells aren't smooth, they're twisted and knotted like cosmic shoelaces, evidence of powerful magnetic fields shaping the outflow. Meanwhile, the outermost layers stretch nearly 3 light-years across, suggesting these eruptions began over 1,500 years ago. But here's the real puzzle: stellar deaths typically happen in one grand finale, not this stop-start pattern. Astronomers suspect the cat's eye's central star might have had help. One leading theory points to an unseen binary companion, a second star whose gravitational tug could trigger periodic eruptions. Alternatively, the dying star itself could have pulsated in its death throes, like a pot boiling over in slow motion. Each expansion and contraction would have peeled away layers of its atmosphere, launching material outward in waves. What makes the cat's eye truly special is how it preserves these eruptions in perfect sequence. Unlike most nebulae where winds and radiation blur the past, here, each shell remains distinct, a celestial fossil record. By studying the spacing and chemistry of these layers, astronomers can literally read the star's final chapters, revealing not just how it died, but how it fought to survive. So next time you see an image of the cat's eye, don't just admire its beauty, count the rings. Each one is a timestamp from a star's violent history, proving that even in death, the universe loves a dramatic encore. Just when you think you've seen the strangest shapes in space, the Southern Crab Nebula takes cosmic weirdness to another level. Officially catalogued as HEN 2104, this nebula looks less like a crab and more like an enormous hourglass gripped by 2 skeletal hands. Those eerie, claw-like structures stretching outward aren't just for show. They're the result of a violent celestial tango between 2 stars locked in a gravitational embrace. At the heart of this spectacle lies a dying red giant star and its smaller, denser companion, a white dwarf. The red giant, bloated and unstable, is shedding its outer layers into space, while the white dwarf's intense gravity whips this material into 2 vast, opposing jets. These jets carve through the surrounding gas like cosmic blowtorches, sculpting the nebula's distinctive legs. But here's where it gets wild: the entire structure isn't steady. The 2 stars orbit each other in a tight, erratic dance, causing the jets to wobble and spiral over time. The result, those twisted, outstretched filaments that seem to clutch at the void. Hubble's sharp eye revealed even more drama. The nebula's central region isn't smooth, it's a chaotic knot of gas and dust glowing fiercely under the white dwarf's ultraviolet radiation. Meanwhile, the outer claws stretch nearly half a light-year across, their tips glowing with shock waves as they slam into slower-moving material. This isn't just a static sculpture, it's a dynamic, evolving battlefield where 2 stars compete for dominance, hurling gas at speeds of hundreds of kilometers per second. What makes the Southern Crab truly unique is how perfectly it illustrates the concept of a symbiotic star system. Most planetary nebulae form from a single dying star, but here the white dwarf isn't just a bystander, it's an active participant, stealing material from its red giant partner. Occasionally, this stolen gas builds up on the white dwarf's surface until it detonates in a miniature thermonuclear explosion, brightening the entire system temporarily. Astronomers call these events recurrent nova, and they might explain why the Southern Crab's lobes appear so lumpy and uneven. Each eruption adds another layer of complexity to the chaos. The nebula's bizarre shape also raises a tantalizing question. Could this be a glimpse of our own sun's future? In about 5 billion years, the Sun will swell into a red giant, and while it doesn't have a binary companion, its death throes might still produce intricate structures. Studying systems like the Southern Crab gives us a front-row seat to the processes that shape planetary nebulae and reminds us that even in the coldest reaches of space, the universe has a flair for the dramatic. So next time you see an image of this cosmic crustacean, remember, those ghostly claws aren't just random twists of gas. They're the signature of two stars locked in a gravitational struggle, painting their masterpiece across the cosmos one violent outburst at a time. Moving from the dramatic dance of the Southern Crab Nebula, we stumble upon a cosmic anomaly that defies everything we know about temperature, the Boomerang Nebula. Imagine stepping into a place colder than the void of space itself, a chilling -272 degrees Celsius. That's just 1 degree above absolute zero, the theoretical limit where all motion stops. This isn't science fiction, it's the Boomerang Nebula, officially the coldest known natural location in the entire universe. So how does a nebula achieve such an extreme deep freeze? The secret lies in its dying star's frantic last act. At the nebula's core, an aging star, much like our Sun but further along in its death throes, is expelling its outer layers at a staggering speed, nearly 164 kilometers per second. That's 10 times faster than the solar wind our Sun produces. As this gas bursts outward, it expands rapidly, cooling down in the process, much like how spraying a can of compressed air makes it icy to the touch. But here, the scale is unimaginably vast. The nebula's expansion is so violent that its gas has cooled to a temperature colder than even the background glow of the Big Bang, which lingers at a relatively balmy -270.4 degrees Celsius. Hubble's observations reveal the boomerang's eerie structure, a nearly symmetrical, bow tie-like shape with faint, elongated lobes stretching over 2 light years. These lobes are the aftermath of that hyper-fast stellar wind, carving through surrounding material and leaving behind a trail of ultra-cold gas. But there's a twist. The nebula isn't just cold, it's unevenly cold. The central regions are slightly warmer, hinting at hidden activity near the dying star, while the outer edges plunge into the deepest freeze. This temperature gradient suggests the star isn't just passively shedding material, it's doing so in bursts like a cosmic geyser with a mind of its own. What makes the boomerang even more puzzling is its age. Most planetary nebulae glow brightly as their central stars heat the ejected gas, but the boomerang star hasn't reached that phase yet. It's caught in a brief, rare moment where the gas is still expanding and cooling, but the star hasn't warmed enough to light it up. This makes the boomerang a cosmic time capsule, offering a snapshot of a planetary nebula's earliest stages. But the real jaw-dropper, the boomerang's cold, isn't just a record, it's a mystery. Even with our understanding of expansion and cooling, the temperatures here are lower than most models predict. Some scientists theorize that the star's magnetic fields or unseen companions might be amplifying the cooling effect, while others suggest we're witnessing a unique alignment of conditions that may never repeat. So next time you shiver on a cold winter night, remember the Boomerang Nebula, where the universe proves it can outdo even our most extreme imaginations. And as we'll soon see, space has even more surprises in store. Now, leaving behind the icy grip of the Boomerang Nebula, let's turn our attention to a cosmic phenomenon that's more like a celestial hall of mirrors, the Egg Nebula. Officially known as CRL 2688, this nebula doesn't just glow. It flickers with ghostly echoes of light, creating concentric rings that ripple outward like ripples on a pond. But in this case, the pond is space itself, and the ripples are starlight bouncing off layers of dust ejected by a dying star. At the heart of the Egg Nebula lies a star not unlike our Sun, though it's in the throes of its final act. As it sheds its outer layers, it doesn't do so evenly. Instead, it puffs out shells of dust and gas in fits and starts, like a cosmic souffle rising and collapsing over time. Each of these dust shells acts like a mirror, reflecting light from the central star. But because the shells are at different distances, the light takes longer to reach some than others, creating a delayed echo effect. Imagine shouting into a canyon and hearing your voice bounce back at you from multiple walls. The Egg Nebula does the same thing, but with light. What makes these light echoes so valuable to astronomers? They're essentially cosmic measuring tapes. By tracking how long it takes for light to travel from the star to each dust shell and back, scientists can calculate precise distances within the nebula. This isn't just about understanding the Egg Nebula itself. It's a proof of concept for measuring distances across space. In a universe where figuring out how far things are is notoriously tricky, light echoes offer a rare, tangible method to map the depths of the cosmos. Hubble's sharp eye has captured these echoes in stunning detail, revealing delicate, onion-like layers that tell the story of the star's violent past. Each ring represents a different eruption, a moment when the star coughed out another shell of material. The outermost rings are older, fading relics of outbursts that happened centuries ago, while the inner ones are fresh, still shimmering with recent activity. Piecing together this timeline lets astronomers reconstruct the star's death throes like reading tree rings to understand a forest's history. But there's a twist. The Egg Nebula's echoes aren't perfect circles. Some are warped or uneven, hinting that the star didn't eject its material symmetrically. This asymmetry could mean the star has a hidden companion tugging at it, or that its magnetic fields are shaping the outflow in unpredictable ways. Either way, it's a reminder that even in death, stars refuse to follow simple rules. So the next time you look up at the night sky, remember the Egg Nebula, a place where light doesn't just travel. It lingers, leaving behind echoes that help us measure the universe itself. And as we'll see, the cosmos has even more ways to bend the rules of light and time. Now, let's shift our gaze to a ghostly relic of the cosmos, the Medusa Nebula, also known as Able 21. Unlike the vibrant, echoing light of the Egg Nebula, this celestial spectre is a whisper in the darkness, so faint that it nearly fades into the backdrop of space. But don't let its dim glow fool you. The Medusa Nebula is a sprawling giant stretching across light years, and its subtle light holds secrets about the final, quiet stages of a planetary nebula's life. What makes the Medusa Nebula so hard to spot? It's ancient. While younger nebulae blaze with the energy of freshly ejected gas, the Medusa has been around for tens of thousands of years. Over time, its material has spread thin, drifting farther from its dying central star. The star itself, now a cooling white dwarf, no longer pumps out enough ultraviolet radiation to ignite the surrounding gas into the bright glow we see in younger nebulae. Instead, the Medusa's faint emission comes from a delicate dance between residual starlight and the thin veil of gas it once expelled. It's like the last embers of a campfire, still warm but barely visible against the night sky. Yet, this faintness is precisely what makes the Medusa so fascinating. It's a snapshot of what all planetary nebulae eventually become, expanded, diluted, and slowly merging with the interstellar medium. Astronomers study nebulae like the Medusa to understand how these structures dissolve back into the galaxy, seeding space with heavier elements forged in their stars' cores. The iron in your blood, the calcium in your bones, these elements were once scattered by nebulae in their final act, just like the Medusa is doing now. Hubble and other telescopes have peeled back the layers of this enigmatic nebula, revealing intricate filaments and knots of gas that tell the story of its turbulent past. These structures are the remnants of violent stellar winds and ejections that happened millennia ago, now frozen in time as they drift apart. Some filaments are shockingly well preserved, hinting that even in its old age, the Medusa's structure is more complex than its faint appearance suggests. One of the biggest surprises, the Medusa isn't alone. Its central star seems to have a companion, a faint, cool star orbiting nearby. This binary pairing might explain why the nebula's structure isn't perfectly symmetrical. Over eons, the gravitational tug-of-war between the two stars could have twisted the outflowing gas into the intricate web we see today. It's a reminder that even in death, stars rarely go quietly, and their cosmic partnerships leave lasting marks. The Medusa Nebula is more than just a fading glow. It's a cosmic history book, its pages written in gas and time. By studying its subtle light, astronomers piece together the final chapters of stellar evolution, uncovering how the universe recycles its ingredients for new generations of stars and planets. And as we'll see next, the cosmos has even more ways to surprise us with its twilight wonders. Moving from the ancient whispers of the Medusa Nebula, let's turn our attention to a cosmic sculpture with a strikingly different personality, the Ant Nebula. Officially known as Menzel 3, this nebula earns its nickname from its uncanny resemblance to an ant's segmented body, complete with twin lobes that mimic a head and thorax. But this isn't just a playful twist of cosmic geometry. The Ant Nebula's bizarre shape is a cosmic detective story, pointing to violent interactions between stars and the invisible hand of gravity shaping their aftermath. What makes the Ant Nebula's structure so unusual? Unlike many planetary nebulae which expand in relatively symmetrical shells, this one boasts two distinct, fast-moving jets shooting outward in opposite directions. These twin outflows, traveling at speeds of hundreds of kilometers per second, carve the nebula's ant-like silhouette. But here's the twist: such precise, high-speed jets rarely form around solitary stars. Astronomers suspect a hidden companion star orbits the dying central star, its gravity funneling ejected material into these narrow, focused beams. It's like a cosmic sprinkler with the companion star's pull directing the flow. Hubble's sharp eye has revealed even more clues. The Ant Nebula's lobes aren't smooth. They're studded with knots and filaments, suggesting episodes of erratic mass loss from the central star. Some of these structures curve dramatically, as if sculpted by powerful magnetic fields or shock waves from stellar collisions. And nestled at the nebula's heart lies the central star itself, a hot, white dwarf that's still pumping out intense radiation, lighting up the surrounding gas like a neon sign. Yet, despite its brilliance, this star's partner remains elusive, detected only indirectly through the nebula's imbalanced motions. The Ant Nebula's chaos might also hint at a recent catastrophic event. Some theories propose that the dying star swallowed its binary companion, or at least came dangerously close. As the star expanded into a red giant, it could have engulfed the smaller star, which then spiraled inward, ejecting material in opposing jets before either merging or surviving as a stripped-down remnant. This gravitational tug-of-war would explain the nebula's explosive asymmetry and the high-energy shocks rippling through its gas. But the Ant Nebula isn't just a relic of destruction. Its twin jets are seeding space with heavy elements, and its intricate structure serves as a blueprint for understanding how binary stars shape their surroundings. By studying its lobes, astronomers gain insights into the mechanics of mass transfer between stars, the role of magnetic fields in directing outflows, and even the origins of some exotic stellar remnants. As we peel back the layers of this cosmic anthill, we're reminded that even the strangest shapes in space tell a story, one of partnership, chaos, and the delicate balance of forces that govern the universe. And just when we think we've unraveled its mysteries, the cosmos prepares another surprise. Up next, we'll encounter a nebula that's vanishing before our eyes, a celestial phenomenon that defies even the most careful predictions. Now, shifting our gaze from the Ant Nebula's explosive symmetry, we encounter a cosmic enigma that's slipping away before our very eyes, the Stingray Nebula. This celestial wonder, catalogued as Hen 31357, holds a record no other nebula can claim. It's the youngest known planetary nebula, and it's vanishing at an astonishing pace. Just 2 decades ago, the stingray shone with a vivid blue-green glow, its delicate tendrils resembling the graceful fins of its namesake. But recent observations reveal a startling transformation. The nebula has faded to a mere shadow of its former self, dimming by a factor of nearly 100 since the 1990s. For comparison, most planetary nebulae take thousands of years to fade noticeably, yet the stingray has done so in less than a human lifetime. What cosmic switch flipped to cause such a rapid decline? The answer may lie in the nebula's central star, a hot, compact remnant that's the engine behind the stingray's glow. As the star exhausts its nuclear fuel, it cools and contracts, reducing the ultraviolet radiation that lights up the surrounding gas. Normally, this process unfolds over millennia, but the stingray star appears to be collapsing at breakneck speed. Some astronomers suggest it might be crossing a critical threshold, transitioning from a phase of intense activity to a quieter, dormant state far sooner than expected. Imagine a light bulb flickering out decades ahead of schedule. It defies everything we know about stellar retirement. Hubble's observations add another layer of intrigue. The nebula's structure, once crisp and well-defined, now appears patchy and uneven. Gas clouds that once fluoresced brightly have grown faint, as if the star's light can no longer reach them. Even more puzzling, the nebula's outer edges seem to be dissolving faster than its core, a phenomenon that challenges standard models of nebula evolution. Could magnetic fields or unseen companions be accelerating this dissolution? Or is the star's cooling so abrupt that it's effectively switching off entire regions of the nebula at once? One leading theory points to the stingray's youth as the key to its rapid fade. Born from a star that only recently shed its outer layers, the nebula's gas is still relatively dense and compact. Without the buffer of time to expand and thin out, even small changes in the central star's output have dramatic effects on the nebula's brightness. It's like blowing out a candle in a small room. The flame's disappearance is instantly noticeable, whereas in a vast hall, the change would be subtle. Yet the stingray's behavior raises bigger questions. If some stars can collapse and dim this quickly, might there be others we've overlooked because they faded before we could study them? Could this explain why planetary nebulae seem rarer than predicted in certain regions of space? Every flicker from the stingray is a clue, urging astronomers to rethink the timelines of stellar death. As we watch this nebula vanish, we're witnessing a cosmic ephemeral art show, one that reminds us how dynamic and unpredictable the universe can be. Next, we'll unravel another mystery, one where dark matter might be pulling the strings behind a nebula's eerie gaze. Turning our attention from the fading glow of the stingray, we come face to face with one of the night sky's most haunting sights, the Owl Nebula. Catalogued as Messier 97, this ghostly sphere stares back at us with 2 piercing dark voids, earning its nickname and sparking a debate that challenges our understanding of cosmic forces. What lurks behind those eerie eyes? Some researchers dare to suggest an invisible culprit: dark matter. At first glance, the Owl Nebula appears like many other planetary nebulae, a glowing shell of gas cast off by a dying star. But peer closer, and those 2 shadowy patches emerge, each nearly perfectly circular and aligned symmetrically. Most nebulae with such features owe their shapes to binary stars or magnetic fields, yet the Owl's central star shows no evidence of a companion, and its magnetic influence seems too weak to carve such precise voids. This anomaly led astronomers to propose a radical idea. Could dark matter, the universe's most elusive substance, be sculpting these gaps? The theory hinges on dark matter's gravitational pull. If dense clumps of it drifted through the nebula, their gravity might siphon away gas, leaving behind those empty eyes. Simulations show this could work, but there's a catch. Dark matter is notoriously diffuse, rarely clustering tightly enough to create localized effects. For it to shape the Owl's structure, it would need to be concentrated in an unexpected way. perhaps funneled by the dying star's own gravitational field or trapped in ancient, unseen filaments. Critics counter that more mundane explanations fit the data. Turbulent stellar winds or shockwaves from the star's past eruptions could have punched holes in the nebula. Others point to a phenomenon called shadowing, where dense knots of gas near the star block ultraviolet light, creating the illusion of voids. Still, the dark matter hypothesis persists because of one stubborn detail: the owl's eyes are too uniform. Natural chaos should make such symmetrical structures vanishingly rare, yet there they are, gazing coldly across the cosmos. Adding to the intrigue, the Owl Nebula lies relatively close to our galaxy's plane, a region where dark matter is thought to pool more densely. If the theory holds, studying this nebula could offer a unique way to map dark matter's distribution, using a dying star's final breath as a cosmic detector. Whether the answer lies in shadowy particles or stellar physics, the owl's unblinking stare reminds us how much we still don't understand. Up next, we'll examine a nebula where polar vortices twist gas into shapes that defy imagination. Now, let's venture into the mesmerizing realm of the Saturn Nebula, where celestial artistry takes an unexpected turn. Catalogued as NGC 7009, this striking nebula earned its name not just for its resemblance to the ringed planet, but for something far more peculiar: its bizarre polar vortices. These ANSI, as astronomers call them, stretch outward like ethereal handles, defying the usual chaos of stellar death with their eerie symmetry. At the heart of this cosmic spectacle lies a dying star, furiously expelling its outer layers into space. But unlike the turbulent, uneven gusts seen in most planetary nebulae, the Saturn Nebula's winds seem choreographed. High-speed stellar winds, racing at hundreds of kilometers per second, collide with slower-moving gas ejected earlier in the star's death throes. This clash creates shockwaves that sculpt the ANSI, those glowing, handle-like extensions at either pole. What's baffling is their precision. They nearly mirror images of each other, as if shaped by an invisible cosmic lathe. One leading theory suggests magnetic fields play the role of the sculptor. As the star spins, its magnetic field channels the outflowing winds into tight jets, funneling them poleward. This focused ejection could explain the ANSI's sharp, linear structure, but there's a twist. Observations reveal the central star isn't spinning nearly fast enough to generate the required magnetic strength. So, what's whipping these winds into such disciplined shapes? Some researchers propose a hidden companion star, its gravity stirring the pot and creating the conditions for these polar vortices. Yet, no such companion has been definitively detected. Another puzzle lies in the ANSI's composition. Spectroscopic studies show they're rich in nitrogen and oxygen, elements typically forged deep within stars. Their presence in these distant structures hints at a violent past, perhaps episodes of explosive helium burning that hurled material far beyond the star's surface before the nebula formed. The Saturn Nebula might not just be dying gracefully, it could be telling the story of its own explosive tantrums frozen in time. Adding to the intrigue, the ANSI aren't static. Hubble images taken years apart reveal subtle changes in their structure, suggesting the stellar winds are still actively reshaping them. This dynamism offers a rare chance to watch stellar evolution in action, like catching a painter mid-stroke on a cosmic canvas. The Saturn Nebula's mysteries don't end there. Its football-shaped core, wrapped in a delicate blue-green glow, hints at even more complex physics at play. Some models suggest the star's ultraviolet radiation is ionizing the gas unevenly, creating pressure differences that further sculpt the nebula's form. Every layer of this celestial onion peels back to reveal new questions. As we marvel at these polar vortices, we're reminded that even in death, stars refuse to be predictable. Up next, another nebula with layers of secrets where twin shells whisper tales of a star's explosive past. Now, let's turn our gaze to a nebula that wears its history like a cosmic onion, the ghost of Jupiter. Officially catalogued as NGC 3242, this eerie glow might resemble the gas giant in amateur telescopes, but its true intrigue lies in what's hidden beneath the surface. Unlike most planetary nebulae which flaunt a single, chaotic shell of gas, the ghost of Jupiter boasts two distinct layers like a celestial matryoshka doll. This rare double shell structure whispers a story of a star that didn't die quietly but erupted in multiple violent outbursts. The inner shell, a vivid blue-green ring, glows fiercely under the ultraviolet rage of the nebula's central white dwarf. This compact layer is the star's most recent farewell, a burst of gas ejected just a few thousand years ago, still ionized and luminous. But step back and you'll spot the outer shell, a vast, faint halo stretching twice as far, its delicate filaments barely visible. This ghostly shroud is the relic of an earlier eruption, a slower, older outflow now fading into the void. Together, they paint a timeline of stellar death in two acts. What could trigger such episodic violence? One clue lies in the white dwarf's composition. Spectra reveal it's rich in hydrogen, unusual for a star that shed its outer layers. This suggests the star didn't expel all its material at once. Instead, it might have paused between outbursts, briefly reigniting nuclear reactions in a final, fitful struggle against collapse. Imagine a candle sputtering back to life before its last flicker. This star's death throes were anything but orderly. Another twist comes from the shell's shapes. The inner ring is nearly perfect, a testament to symmetrical ejection, while the outer halo is slightly lopsided. This mismatch hints at a changing axis of rotation or even a hidden companion star tugging asymmetrically on the dying star's winds. Some researchers propose the outer shell was sculpted by interstellar drag, as the nebula plowed through uneven cosmic dust. Either way, the ghost of Jupiter's layers are more than just aesthetic, they're forensic evidence of a turbulent demise. Hubble's sharp eyes have caught even finer details, tiny knots and jets embedded within the inner shell, likely formed by shockwaves from the white dwarf's relentless winds. These structures, barely wider than our solar system, are evolving in real time, offering a front-row seat to how stellar material redistributes after expulsion. Meanwhile, the outer shell's faint glow, rich in nitrogen, suggests the star's earlier outbursts were chemically distinct, another puzzle for theorists. The ghost of Jupiter's double shell isn't just a curiosity. It challenges the textbook model of planetary nebula formation, where a single, smooth ejection was thought to dominate. Here, we see a star that refused to follow the script, staging multiple encores before its final bow. As we unravel these layers, we're reminded that even in the cold depths of space, death isn't always a one-time event. Up next, a nebula that trades ghostly whispers for sparkling brilliance, where clusters of cosmic gems dangle like a celestial necklace. Now, let's trade ghostly layers for celestial dazzle as we uncover the Necklace Nebula, a cosmic jewel box glittering with what looks like diamonds strung across the void. Officially labeled PNG 054.2-03.4, this nebula's brilliance isn't just for show. It's a masterclass in stellar teamwork. At its heart lies not one but two stars locked in a tight orbital dance, and their partnership has crafted one of the most photogenic structures in the cosmos. Those dazzling gems aren't precious stones, of course they're dense knots of gas, each about twice the mass of Earth, glowing fiercely under the ultraviolet spotlight of the binary system. Imagine a string of pearls, each one fluorescing like a neon sign, and you've got the Necklace Nebula's signature look. This radiant display happens because the primary star, a bloated giant, once engulfed its smaller companion. As the duo spiraled closer, the giant's rotation sped up, flinging material outward in a furious equatorial disk, like a spinning dancer tossing her skirt into a perfect ring. Over time, instabilities in this disk fragmented it into those luminous clumps we see today. Hubble's close-ups reveal even wilder details. The diamonds aren't evenly spaced, some cluster like grapes while others stand alone, hinting at turbulence during their formation. And their glow isn't uniform. The ones nearest the binary stars shine brightest, bathed in the most intense UV radiation, while others flicker more faintly. This gradient tells us the knots are slowly evaporating, their material eroding under the star's relentless glare. Yet despite this erosion, the densest knots might survive for thousands of years, outliving the nebula itself. The binary system at the center adds another twist. The smaller star, likely a white dwarf, isn't just a passive spectator. It's stealing material from its partner, creating violent accretion loops and jets that further sculpt the nebula. Some astronomers speculate these interactions triggered the disk's fragmentation in the first place, making the necklace a testament to how stellar duets can warp their surroundings. But here's the real kicker: the entire nebula is staggeringly young. The gas knots suggest the ejection event happened a mere 5,000 years ago, a blink in cosmic time. That's why the necklace still looks so crisp, with none of the fading or distortion seen in older nebulae. It's like catching a supernova's aftermath in high definition, giving us a front-row seat to stellar evolution's most flamboyant acts. What's next? A nebula where elegance gives way to outright chaos, a cosmic gourd erupting with some of the fastest gas surges ever detected. Now, let's step away from cosmic jewels and into a celestial storm. The Calabash Nebula, where beauty isn't found in symmetry but in sheer, unbridled violence. Officially catalogued as OH2 31.8 plus 0 4.2, this nebula is anything but serene. It's a cosmic pressure cooker, a star in the throes of a spectacular tantrum as it hurtles through one of the most dramatic transitions in stellar evolution, from a bloated red giant to a planetary nebula. At its core, the star is shedding its outer layers at mind-bending speeds, ejecting gas at 700,000 kilometers per hour. To put that in perspective, at that velocity, you could race from Earth to the Moon in just under 20 minutes. This isn't a gentle shedding. It's a full-blown eruption with shockwaves rippling through the surrounding space, heating the expelled material to incandescent temperatures. The result, a chaotic, hourglass-shaped nebula that looks more like a celestial explosion frozen in time than the graceful rings or shells we've seen elsewhere. What makes the Calabash so unique is its stage of transformation. We're catching it right in the middle of its metamorphosis, a phase so brief that astronomers consider it a cosmic stroke of luck to witness. The central star, still hidden within a thick shroud of dust and gas, is furiously trying to stabilize itself. Meanwhile, the ejected material isn't spreading evenly. Instead, it's clumping into dense, fast-moving lobes, creating the nebula's distinctive, gourd-like shape that earned it the nickname the Rotten Egg Nebula, due to its sulfur-rich composition. But the drama doesn't stop there. The Calabash's central star is a ticking time bomb. As it continues to shed mass, it's inching closer to becoming a white dwarf, but the process is anything but smooth. The star's violent outbursts have created a turbulent environment where gas and dust collide, generating powerful shock fronts that glow in eerie greens and reds. Infrared observations have revealed intricate structures within the nebula-tangled streams of material, some being dragged back toward the star by gravity, while others are flung outward with enough force to escape entirely. And here's the twist: this chaos might hold clues to how planetary nebulae form in the first place. The Calabash challenges the old assumption that these structures emerge from a slow, steady shedding of a star's outer layers. Instead, it suggests that some stars go out with a bang, or rather, a series of them catapulting their material into space in violent, uneven bursts. Up next, we'll trade turbulence for an unexpected glow, a nebula where oxygen takes center stage in a dazzling display that defies expectations. Now, let's shift from the Calabash Nebula's fiery tantrums to a far more serene but equally puzzling sight, the Blue Snowball Nebula, a cosmic gem that glows with an otherworldly blue hue. Catalogued as NGC 7662, this nebula might look tranquil at first glance, but don't be fooled. Its stunning color comes from an unexpected source: intense oxygen emissions that have left astronomers scratching their heads. Most planetary nebulae shine brightest in hydrogen and nitrogen, but the blue snowball defies expectations by putting oxygen in the spotlight. This isn't just a subtle glow, it's a dazzling, almost electric blue radiance that dominates the nebula's structure. How did oxygen, typically a background player in these cosmic spectacles, steal the show? The answer lies in the unique conditions of its central star. Unlike many dying stars that shed their outer layers gently, this one has exposed its hot, dense core much faster, heating the surrounding gas to extreme temperatures. At over 100,000 degrees, the star's ultraviolet radiation energizes oxygen atoms, causing them to emit that iconic blue light. But here's where things get even stranger. The blue snowball isn't just glowing with oxygen, it's practically bathing in it. Observations reveal oxygen concentrations far higher than predicted, suggesting the nebula's chemistry is unlike anything we've seen before. Some theories propose that the star's rapid evolution dredged up deep layers of oxygen-rich material from its interior, while others speculate that the nebula's structure traps and concentrates oxygen in ways we don't yet understand. Either way, it's forcing scientists to rethink how elements are distributed in planetary nebulae. Zooming in, the nebula's intricate layers add to the mystery. Its outer shell, faint and wispy, contrasts sharply with the vibrant inner ring, where the oxygen glow is most intense. This layered structure hints at multiple ejection events, each leaving behind a different chemical fingerprint. And nestled at the center, a white dwarf so hot it's almost invisible to optical telescopes, radiating the energy that powers this entire luminous display. What makes the blue snowball particularly fascinating is its defiance of the cosmic norm. Planetary nebulae are often considered predictable in their composition, but this one throws the rulebook out the window. It's a reminder that even in death, stars can surprise us, revealing secrets about their lives and the universe's chemistry that we never saw coming. Next up, we'll marvel at a nebula where symmetry isn't just beautiful, it's almost unnervingly precise. Stepping away from the blue snowball's unexpected chemistry, we arrive at a nebula where nature's precision feels almost artistic, the Twin Jet Nebula. Officially known as Messier 29, this stunning structure looks less like a cosmic accident and more like a carefully crafted masterpiece, with two symmetrical jets shooting outward like the wings of a celestial butterfly. What's behind this breathtaking symmetry? The answer lies in a delicate gravitational dance between two stars locked in a tight orbit. Most planetary nebulae are messy, their shapes twisted by turbulent stellar winds, but the Twin Jet Nebula defies the chaos. Its near-perfect bipolar lobes stretch over 1 light-year across, each mirroring the other with uncanny precision. This isn't just a coincidence, it's the result of a binary star system at its heart. As the primary star shed its outer layers, its companion star's gravity sculpted the ejected material into those iconic jets, channeling the gas into two narrow, opposing streams. Think of it like a spinning garden sprinkler where the water sprays in predictable arcs, except here, the sprinkler is a dying star and the water is superheated gas racing at hundreds of kilometers per second. But the Twin Jet Nebula's symmetry goes even deeper. Hubble Space Telescope observations reveal intricate, spiral-like patterns within the jets, suggesting the stars aren't just orbiting, they're wobbling. This subtle motion, called precession, causes the jets to twist slowly over time, carving out intricate corkscrew shapes in the surrounding gas. It's a cosmic fingerprint, revealing the star's exact orbital dynamics. Scientists estimate the binary pair completes an orbit every 120 years, and with each pass, they leave another mark on the nebula's evolving structure. What's truly remarkable is how the Twin Jet Nebula challenges our assumptions about stellar deaths. Typically, a single star's demise creates disordered, asymmetric nebulae, but here, the presence of a companion star imposes order on the chaos. The second star acts like a director, orchestrating the outflow of material with such precision that the result looks almost engineered. Some researchers even compare it to a cosmic hourglass, with the binary system sitting at the narrow waist, regulating the flow of gas in both directions. Zooming in closer, the nebula's core holds another surprise, a thick, dusty disk encircling the stars. This disk isn't just debris, it's the engine fueling the jets. As material spirals inward toward the stars, some of it gets funneled upward and downward along magnetic field lines, launching the jets we see today. Without this disk, the twin-jet nebula's symmetry would collapse into the usual stellar chaos. The twin-jet nebula doesn't just dazzle with its beauty, it offers a rare glimpse into the invisible forces shaping our universe. Every ripple, every curve in its structure tells a story of gravitational teamwork, proving that even in the vast, unruly cosmos, there's room for perfect harmony. Up next, we'll encounter a nebula that looks like it's been kicked across the cosmos, its shape warped by forces we're only beginning to understand. After marveling at the twin-jet nebula's symmetrical perfection, we shift our gaze to a cosmic structure that couldn't be more different, the Football Nebula. Officially catalogued as NGC 2440, this nebula earns its nickname not just from its oval outline, but from the way it appears to have been violently twisted, as if some unseen force punted it across the galaxy. Unlike the orderly jets of the twin-jet nebula, the Football Nebula's chaotic form tells a story of turbulence, its shape warped by the erratic motion of its central white dwarf star. At first glance, the Football Nebula might seem like just another planetary nebula, but a closer look reveals its bizarre, almost shredded appearance. Instead of smooth, symmetrical lobes, its gas clouds stretch into jagged, irregular streamers, fanning outward like the frayed ends of a rope. This isn't the gentle death of a star, it's a stellar explosion caught in mid-action, frozen in time. The key to this chaos lies in the nebula's white dwarf, one of the hottest known, blazing at over 200,000 degrees Celsius, but temperature alone doesn't explain its distorted shape. The real culprit, motion. Unlike most planetary nebulae where the central star sits relatively still, the white dwarf in NGC 2440 is racing through space, dragging its ejected layers along with it. Imagine a speeding car with its doors flung open, scattering debris behind it in a messy trail. That's essentially what's happening here. As the dying star expelled its outer layers, it didn't do so evenly. Instead, it hurled material in multiple outbursts, each eruption blown sideways by the star's own movement. The result is a nebula that looks like it's been stretched and smeared across the cosmos. Hubble Space Telescope images reveal even more peculiar details. The Football Nebula's core is surrounded by dense, knotty structures, some of which resemble tiny comets. These aren't actual comets, of course, but clumps of gas and dust sculpted by the white dwarf's fierce radiation and stellar winds. They're like cosmic breadcrumbs marking the path of the star's tumultuous journey. Meanwhile, the nebula's outer regions are littered with faint, looping filaments, ghostly remnants of older ejections, now being overtaken by newer, faster-moving material. What makes the Football Nebula truly fascinating is what it reveals about stellar death. Most stars shed their outer layers in a relatively orderly fashion, creating nebulae with recognizable shapes. But when a star is in motion, like the one at the heart of NGC 2440, the rules change. Its movement disrupts the symmetry, turning what could have been a smooth, spherical shell into a tangled mess. This suggests that the environment around a dying star, whether it's moving, orbiting another star, or caught in a stellar wind, can dramatically alter its final act. The Football Nebula also challenges the idea that planetary nebulae are fleeting phenomena. While many fade within tens of thousands of years, NGC 2440's complex structure hints at a longer, more violent life. Its multiple layers of ejected material suggest the star didn't die quietly in one dramatic event, but instead experienced several violent episodes, each leaving its mark on the nebula's evolving form. It's a reminder that even in death, stars can be unpredictable, their endings as unique as their lives. Up next, we'll encounter a nebula so intricately textured, it looks like it's wrapped in cosmic fur, a structure that defies expectations in its own wild way. Leaving behind the chaotic swirl of the football nebula, we now turn our attention to a cosmic masterpiece that looks almost alive. Meet the Eskimo Nebula, officially known as NGC 2392, a stunning planetary nebula whose delicate, fur-like filaments seem to ripple outward like the ruffled hood of a parka. At first glance, this nebula appears serene, even playful, but don't be fooled. Its intricate texture is the result of violent stellar winds and radiation carving through space like an invisible sculptor. What makes the Eskimo Nebula stand out is its uncanny resemblance to a face surrounded by a furry collar. The face itself is the nebula's bright inner shell, a bubble of glowing gas illuminated by its central star's intense ultraviolet light. But the real showstopper lies just beyond a halo of densely packed, streamer-like filaments that fan outward in perfect radial symmetry. These aren't random wisps of gas, they're meticulously shaped by forces more turbulent than a blizzard. Zooming in with the Hubble Space Telescope reveals the secret behind this cosmic fur. The filaments are actually dense knots of gas and dust, each one stretching nearly a light year long. They formed when the dying star at the nebula's core began shedding its outer layers in erratic bursts. Unlike the gentle, steady outflows seen in other nebulae, this star unleashed gusts of stellar wind at speeds exceeding 150,000 kilometers per hour. These winds collided with slower-moving material ejected earlier, crushing and stretching it into those distinctive hair-like strands. But there's another twist. The Eskimo Nebula's central star isn't just blowing out gas, it's also bathed in a fierce barrage of radiation. This radiation heats the surrounding material, causing it to glow in vivid hues of blue and green while also ionizing the gas, further sculpting those filaments into their intricate patterns. It's a relentless tug of war between creation and destruction, with radiation and wind working in tandem to shape the nebula's haunting beauty. What's even more remarkable is the nebula's layered history. The inner shell, which forms the face, is relatively young, likely ejected within the last few thousand years. But the outer filaments tell a different story. They're remnants of older eruptions, now frozen in time as they drift farther from the star. This two-tiered structure gives astronomers a rare snapshot of stellar evolution, capturing multiple phases of a star's death in a single, breathtaking image. The Eskimo Nebula challenges our assumptions about how planetary nebulae form. Unlike the symmetrical rings or bipolar jets seen in others, its structure is a testament to the raw, chaotic power of stellar winds. It's a reminder that even in the cold vacuum of space, there's artistry in the chaos, an entire celestial landscape woven from violence and time. Next, we'll encounter a nebula that defies expectations in the opposite way. Not with wild complexity, but with a simplicity so striking, it's like finding a perfectly cut gem floating in the void. Now, shifting our gaze from the intricate fur of the Eskimo Nebula, we find ourselves drawn to a celestial object that sparkles with youthful energy. The Little Gem Nebula, officially catalogued as NGC 6818, lives up to its name, a dazzling, compact jewel floating in the vastness of space. Unlike the sprawling, ancient nebulae we've explored so far, this one stands out for its almost childlike brilliance, a cosmic teenager glowing with vibrant intensity. What makes the Little Gem Nebula so special is its unusually bright and dense structure. While most planetary nebulae expand and fade over tens of thousands of years, this one appears to be in its prime, radiating light with an almost reckless abundance. Its central star, still burning hot and fierce, bathes the surrounding gas in ultraviolet radiation, causing it to fluoresce in vivid shades of green and blue. The nebula's compact size, just a fraction of the span of its more evolved cousins, suggests it's only a few thousand years old, making it a relative newcomer on the cosmic stage. Peering through telescopes, astronomers have noticed something peculiar about the little gem's shape. Instead of the chaotic filaments or symmetrical rings seen in older nebulae, this one displays a smooth, slightly elongated shell. This hints at a more orderly ejection of material from its central star, as if the star had a brief but well-behaved tantrum, shedding its outer layers in a controlled burst. The gas is so densely packed that even from hundreds of light-years away, the nebula appears almost solid, like a glowing marble suspended in the dark. But don't let its polished appearance fool you. The little gem hides fascinating dynamics beneath its surface. High-resolution observations reveal subtle ripples and knots in its gas, evidence of collisions between faster-moving material and slower, older ejecta. These interactions create shock waves that heat the gas, adding to the nebula's radiant glow. It's like watching a young star's outbursts frozen in time, capturing the moment when instability gives way to stunning beauty. One of the most intriguing theories about this nebula is that its central star might be part of a binary system. The gravitational tug of a companion could explain the nebula's slight asymmetry, as well as the star's ability to expel its outer layers so efficiently. If true, it would mean the little gem's brilliance isn't just a solo act, it's the result of a cosmic partnership, a dance of destruction and creation playing out on a stellar scale. What's equally mesmerizing is how this nebula challenges our understanding of planetary nebula evolution. Most of these objects take millennia to form their iconic shapes, but the little gem seems to have achieved its signature glow in record time. It's as if the star couldn't wait to show off, rushing through its death throes to leave behind this luminous keepsake. As we marvel at the little gem's radiance, we're reminded that not all stellar deaths are slow, drawn-out affairs. Some are quick and dazzling, leaving behind celestial snapshots of youthful energy frozen in space. Up next, we'll encounter a nebula whose patterns seem almost too perfect, as if drawn by the hand of an artist rather than the chaos of the cosmos. Now, as we transition from the youthful glow of the little gem nebula, let's turn our attention to a cosmic marvel that seems plucked straight from an artist's sketchbook, the Spirograph Nebula. Officially known as IC 418, this planetary nebula dazzles with geometric precision, its intricate patterns so symmetrical they almost defy the randomness of space. Unlike the chaotic swirls of many nebulae, the spirograph's design is startlingly orderly, as if drawn by an unseen hand wielding a celestial compass. The Spirograph Nebula gets its name from its resemblance to the looping, interwoven patterns created by the classic drawing toy. Its delicate, lace-like rings ripple outward in near-perfect concentric circles, each layer glowing with vivid hues of red and blue. But how does a dying star produce such precise, almost mathematical beauty? The answer lies in the rhythmic pulsations of its central star, a white dwarf that's still shedding layers of its former self. As the star exhales material into space, it does so in bursts like a heartbeat ejecting gas in regular intervals. These stellar pulses create shock waves that sculpt the surrounding gas into those mesmerizing rings. Imagine dropping pebbles into a pond at steady intervals. Each ripple expands outward, meeting the others to form an intricate interference pattern. That's exactly what's happening here, but on a cosmic scale, with stellar winds acting as the pebbles and the nebula's gas as the water. What's even more fascinating is the nebula's subtle imperfections. High-resolution images reveal that the rings aren't perfectly uniform. Some are thicker, others slightly warped. These quirks hint at turbulence in the star's ejection process, moments when the heartbeat faltered or the stellar winds gusted unpredictably. It's a reminder that even the most orderly cosmic phenomena have hidden complexities, a blend of precision and chaos that makes the Spirograph Nebula so compelling. One theory suggests the central star might be rotating unusually fast, flinging material outward in a spiral rather than a smooth outflow. This could explain why some rings appear denser on one side, as if the star's spin imprinted its motion onto the nebula. Another possibility is the influence of a companion star, its gravity subtly tugging at the ejector to create those intricate loops. Whatever the cause, the result is a nebula that looks less like a natural formation and more like a carefully crafted masterpiece. The Spirograph Nebula also challenges our assumptions about how planetary nebulae evolve. Most expand in a relatively predictable manner, but IC418's patterned structure suggests its growth was anything but random. It's as if the star left behind a cosmic fingerprint, a unique signature etched into the fabric of space. As we marvel at this celestial spirograph, we're reminded that the universe has an uncanny way of blending artistry with astrophysics. Up next, we'll encounter a nebula so perfectly round it seems almost too simple until we peer closer and uncover the secrets hidden within its pristine shape. Shifting our gaze from the intricate geometric patterns of the Spirograph Nebula, we encounter a cosmic oddity that stands out for its striking simplicity, the lemon-sliced nebula. Officially catalogued as IC3568, this planetary nebula boasts a near-perfect spherical shape, a rarity in a universe where asymmetrical, twisted structures are the norm. Its nickname comes from its crisp, clean appearance, resembling a slice of lemon floating in the darkness of space. But don't let its straightforward look fool you. This nebula holds secrets that challenge our understanding of how these celestial objects form. Most planetary nebulae are anything but symmetrical. Their shapes are often distorted by powerful stellar winds, magnetic fields, or the gravitational tug of companion stars, resulting in bipolar jets, twisted filaments, or chaotic lobes. Yet the lemon-sliced nebula defies these expectations, presenting itself as a nearly flawless sphere of glowing gas. This unusual uniformity suggests that its central star experienced a remarkably calm and steady transformation, shedding its outer layers in a smooth, even outflow rather than the violent eruptions seen in other nebulae. The key to its perfect shape lies in the delicate balance of forces at play. Unlike the turbulent ejections that create complex structures elsewhere, the lemon-slice's central star seems to have expelled its material in a gentle, continuous stream. Imagine blowing up a balloon with slow, even breaths. The result is a smooth, round shape. That's essentially what happened here, with stellar winds acting as the steady breath that inflated this cosmic bubble. But there's more to this nebula than meets the eye. High-resolution observations reveal subtle ripples in its outer layers, like faint waves frozen in time. These slight imperfections hint at minor disturbances in the star's final stages, perhaps caused by weak magnetic fields or faint stellar pulsations. Even in this seemingly serene nebula, the universe leaves traces of its inherent unpredictability. One prevailing theory suggests the lemon-sliced nebula's simplicity could be due to the absence of a companion star. Many asymmetrical nebulae are shaped by the gravitational dance of binary systems, but IC3568 might have formed in isolation, allowing its central star to shed material without interference. Another possibility is that the star's rotation was unusually slow, preventing the chaotic ejection pattern seen in faster spinning stars. What makes this nebula particularly fascinating is its defiance of the odds. Planetary nebulae are supposed to be messy, shaped by the violent death throes of their stars. Yet the lemon-sliced nebula stands as a quiet counterpoint, a reminder that even in the chaos of space, elegance can emerge. Its pristine form offers astronomers a unique laboratory to study the quieter, less explosive pathways of stellar evolution. As we peel back the layers of this cosmic lemon, we're left with a profound question: how many other perfectly round planetary nebulae are out there, hidden in the vastness of space, waiting to be discovered? Up next, we'll explore a nebula with an entirely different kind of precision, one sculpted not by calm winds, but by the invisible hand of magnetism. Moving from the serene simplicity of the lemon-sliced nebula, we now turn our attention to a celestial structure so precisely sculpted that it seems almost intentional, the engraved Hourglass Nebula. Officially known as Mycen 18, this stunning nebula earns its name from the uncanny resemblance it bears to an hourglass, with two symmetrical lobes pinched at the center as if shaped by an unseen cosmic hand. While many planetary nebulae display chaotic, sprawling forms, this one stands out for its razor-sharp symmetry, leading astronomers to suspect that something extraordinary, perhaps powerful magnetic fields, is at work behind its flawless design. The engraved Hourglass Nebula's striking shape isn't just a visual marvel, it's a puzzle that challenges our understanding of stellar death. Most planetary nebulae form when aging stars shed their outer layers, creating expanding shells of gas. But the sheer precision of Mycen 18's structure suggests forces far more organized than random stellar winds. Observations reveal that its central star, a white dwarf, is encircled by a dense equatorial ring of material, while high-speed winds blast outward from its poles, carving the nebula's signature hourglass silhouette. Yet even this doesn't fully explain the crispness of its edges or the near-perfect alignment of its lobes. Here's where magnetism enters the picture. Some researchers propose that the star's magnetic field acts like an invisible mold, funneling ejected material into those tight, symmetrical pathways. Imagine squeezing a balloon at its middle. The trapped air bulges evenly at both ends. Similarly, the magnetic field surrounding the dying star could be constricting its outflowing gas, forcing it into that iconic hourglass shape. Supporting this theory, studies of other nebulae have found that magnetic fields can indeed influence the trajectories of charged particles, sculpting them into orderly patterns amid the chaos of stellar death throes. But the mysteries don't end there. The engraved Hourglass Nebula's vibrant colors, a mix of glowing red nitrogen and blue-green oxygen, reveal another layer of complexity. These hues aren't just for show, they map out regions where different elements were ejected at varying stages of the star's demise. The crisp boundaries between these zones suggest the star's mass loss was episodic yet eerily controlled, as if guided by an unseen rhythm. Perhaps the most tantalizing clue lies in the nebula's narrow waist, the pinched region where the two lobes meet. This peculiar feature hints at the presence of a dense disk of dust and gas around the central star, which could be shielding material from escaping equatorially while allowing polar jets to shoot through unimpeded. If confirmed, this would mean Mycen 18's hourglass shape is the result of a delicate cosmic balancing act, where magnetic fields, stellar winds, and disk dynamics all conspire to create one of the most geometrically perfect objects in the universe. As we marvel at this nebula's precision, we're left to wonder how many other celestial hourglasses are out there, their sands of time silently running out in the depths of space. Next, we'll uncover a nebula so vast and enigmatic that astronomers still debate whether it's a planetary nebula at all. Now, shifting our gaze from the finely sculpted engraved Hourglass Nebula, we encounter a cosmic enigma so elusive that astronomers are still questioning its very identity, the Water Lily Nebula. Officially catalogued as U4, this sprawling, ghostly structure stretches across an astonishing 1,400 light-years, making it one of the largest and faintest nebulae ever observed. Unlike the crisp symmetry of Mycen 18, the Water Lily Nebula drifts through space like a delicate wisp of smoke, its pale tendrils barely visible against the darkness. But don't let its ethereal appearance fool you. This nebula hides secrets that could rewrite our understanding of stellar life cycles. The debate begins with its origins. Most planetary nebulae form when dying stars gently shed their outer layers, creating glowing shells of gas. But the Water Lily Nebula's sheer size and chaotic structure don't quite fit that narrative. Instead, some researchers argue it might be the remnant of a supernova, a violent stellar explosion far more energetic than the quiet demise of a typical planetary nebula's central star. Here's where things get intriguing. At the heart of U4 lies a massive hot star named HR 8119, which some believe could be the culprit behind the nebula's creation. Yet, HR 8119 isn't acting like a typical supernova remnant's central engine. It's not a neutron star or black hole, but a rare type of Wolf-Rayet star, known for blasting out powerful winds at speeds exceeding 2,000 kilometers per second. This raises a tantalizing question. Could the Water Lily Nebula be the result of an entirely different cosmic process? One theory suggests that HR 8119's ferocious winds are carving out the nebula's vast structure, like a cosmic sculptor chiseling away at interstellar gas. Observations reveal that the nebula's delicate filaments are rich in ionized oxygen, glowing a faint blue-green, a signature often linked to shock waves from stellar winds or explosions. But here's the twist: the nebula's geometry doesn't match the symmetrical patterns typically seen in supernova remnants. Instead, its chaotic, knotted strands seem more consistent with the turbulent outflows of a hyperactive star. Adding to the mystery, recent studies have detected faint, fast-moving jets within the nebula, aligning with HR 8119's poles. These jets, traveling at hypersonic speeds, suggest the star might be channeling material in tightly focused streams, a behavior more commonly associated with young stellar objects or planetary nebulae in their early stages. This has led some astronomers to propose a hybrid scenario. What if the Water Lily Nebula represents a transitional phase where a massive star's winds mimic the violence of a supernova without the actual explosion? The implications are staggering. If U4 is indeed a planetary nebula, its unprecedented scale challenges our models of how these structures form. If it's a supernova remnant, its unusual central star defies expectations. And if it's something in between, it could reveal entirely new pathways of stellar evolution. For now, the Water Lily Nebula remains a celestial Rorschach test, a cosmic riddle, inviting us to look deeper and question what we thought we knew. As we wrap up our journey through these 25 strange discoveries, one thing becomes clear: planetary nebulae are far more than dying stars' final breaths. They are cosmic laboratories, each one offering a unique glimpse into the forces that shape our universe. From the breathtaking symmetry of the engraved Hourglass Nebula to the ghostly enigma of the Water Lily, we've journeyed through 25 of the universe's most bewildering cosmic wonders. Each of these planetary nebulae has shattered expectations, revealing that death in the cosmos is anything but quiet or predictable. Whether it's the Butterfly Nebula's supersonic jets, the Boomerang's record-breaking chill, or the Stingray's rapid fade into darkness, these celestial phenomena prove that stars don't just burn out, they go out with fireworks, mysteries, and sometimes a touch of cosmic chaos. Take the Cat's Eye Nebula, with its nested shells whispering tales of a star's violent temper tantrums, or the Calabash Nebula, spewing gas at 700,000 kilometers per hour like a celestial pressure cooker bursting at the seams. Then there's the Southern Crab, its claw-like structures sculpted by a stellar dance so precise it could rival any ballet. These aren't just pretty space clouds, they're cosmic crime scenes, each one preserving clues about the forces that govern the universe. And let's not forget the outliers that blurred the lines entirely. The Water Lily Nebula, stretching across 1,400 light-years, challenges whether it's even a planetary nebula at all. The Owl Nebula's eerie eyes spark debates about dark matter's invisible hand, and the Spirograph Nebula's geometric perfection looks so artificial, you'd almost suspect cosmic engineers were at work. Every discovery we've explored today underscores one truth: planetary nebulae are master illusionists. What looks like a simple ring might hide a football-shaped core. What seems like a fading ember might be a hyperactive star in disguise, So now we turn to you. Which of these 25 cosmic riddles left you the most stunned? Was it the Medusa Nebula's ancient, fading glow, or the necklace's glittering gas diamonds? Maybe the ghost of Jupiter's double shell made you do a double take, or the twin jet symmetry seemed too perfect to be natural. Drop your thoughts in the comments. We're just as curious as you are. And if this deep dive into the universe's strangest finales left you hungry for more, don't forget to hit like, subscribe, and ring that notification bell. The cosmos is full of surprises, and we're just getting started. Until next time, keep looking up.